Good evening, Mega. Can you hear me okay? And can you see the desktop? Very good. I hope you had a great weekend. Tonight, I have to go through what's due this week, and let's do that. So it looks like we've got a lot of things happening this week. The CC Confer question, Chapter 12, the 4 questions from Chapter 12, and we have our last big test before the final this weekend. So it opens Friday and closes Sunday. It's a little longer test, so I have increased the number of hours available. And on Thursday, I'll do a review like I did for Test 2. Any questions on what's due this week? Okay, very good. And I'll be covering these samples with you for the test. I wanted to go over the project teams, and I did get all of the teams information, and I updated it. And I believe, Mega, you're in team 4 or 5. No, I guess you're not. Oh, you're in team 3. Right. Hi, Steve. And you're doing units. Yep. Okay. And Steve, you're in team 5? No. Team 4? Okay. Okay, so what I thought I would do tonight, so that you can get an idea of kind of what other teams have done, is just kind of illustrate a couple of projects and kind of give you an idea of what I'm looking for from the format and things of that nature. Hi, Daniel. Okay, so let's take a look at them real quick. I'm not going to go through the whole thing. I just wanted to illustrate how you might do this. So I have 2 projects. I have one from two years ago. So this was from 2016. And they did Raspbian. Okay. And this is what I would expect. I would like to know the team members and what they did, and if any team member didn't contribute, make a note of that. Because I want to explain how I'm going to do the grading on these things. If a team member never participated, they get 0. Okay? The other team members would all receive the same grade I give the whole project. So the only difference would be that the people that didn't participate, they don't get any credit for this project. That's how I grade. But the way to know that is to have the team leader is going to submit the projects to me. and it's going to be one file. It'll be a Word document. In this case, it's a Word document, or it could be a PDF file, which I'll show you the other example. And then further on in the project, they have a table of contents as to what people did, and you kind of know what different people are participating. Samira did the processor management, Shannon did memory management, and this way I know who's doing what, and I can determine their participation in this by what I'm reading here. Any questions on that? This is a good example. Hi, Kang. I'm just going through a couple of and Vale. Hi. I'm going through a couple of examples of the projects previously done. Now we have one team doing Windows 10. We have 3 teams doing Mac OS, which is unusual, but acceptable. And then we have one team doing Unix. Hi, Karen. Welcome. Okay, so there's one example of a project, and they did the Android system, I believe. Oh, no, this was Debbie Raspbian. A Linux offshoot. Okay. And then the other one I wanted to share with you is they did a PDF file, and it was Android. Oh, and what I wanted to share was the number of pages. This one has 36 pages. This one had not as many pages. It had 25 or 25 pages, and I believe the reason was they didn't do all of the deliverables. One of these groups didn't do all the deliverables. This one did. Looks like they did all the deliverables, and then the resources where they got this information, their sources. Okay. They told us kind of where they got all of their resources, somewhere at the end. Let me check. I think it's at the end, the references. Yeah, see, this is what I'm expecting, the sources. Let me know where you're getting this stuff. No, Omega, it's per deliverable. Yeah. Kang, it's per deliverable. Each deliverable is between 5 and 6 pages. Okay, so this one had a total of 25 pages, including 2 pages of resources. Oh, well, I'm glad we're going through this. That's why I want to make sure that people do understand what's expected. Let me look at the team specifications again. Make sure that it says that. Okay. Okay. Overall expectation, 5 to 6 pages. It doesn't say it clearly. Oh, yeah, it is. 5 to 6, including the diagram, is the optimum per deliverable. So it doesn't quite say it the way I'd like to, but it says it. Okay. I should have started with each deliverable. Maybe that's what I'll rewrite this. Each deliverable is 5 to 6 pages. Okay. All right. Well, that's one project. And this one, Android, I want to have your first page tell me who's doing what. Okay? Who's doing what? And then I think their resources are at the end. They don't have many references here for there. So I think I might have deducted a little for that. I don't really deduct a lot if I see that they've done a good job on it. And this was pretty good. I can't remember what they ended up with on this project. But like I said, I would like to see more references. Now they might have the references on the end of each section. So let me see if that's true. I don't see any references here. So no, that isn't true. So you could either have the references at the end. I'd prefer them all at the end, I think. This one had 7 team members. That's why I kind of expected a little bit more. And the team leader was the one who kind of kept everything going. So if you have 7 people, you as a team leader, you can either do an item, right, or a deliverable, or you can assign them. Any questions? I mean, does this help clarify what I'm kind of looking for? Any questions? Thanks, Nikki. All right. Well, I'm excited to see what you guys produce. Yeah, now what you mean by regular spacing, it's 1.1 in Word. Is if you're using Calibri. The paragraph spacing, I believe, is 1.1. I said 0. Use 0. I think I went through this. Yeah, I'm pretty sure I went through this with you guys. Yeah, I don't want double spacing, just single line spacing. I mean, this was, I believe this was, yeah, regular spacing for the paragraphs. Yeah, they used spacing, and they used regular widths. Margins. Yeah, I don't like double spacing. I personally don't like double spacing. And this guy, these looks like it's Arial 12 would be okay. Calibri 11 would be okay. Yeah, these are all Arial. I do want them to look like one document. So what you guys need to do is to make sure that it comes in as one document, even though you are 5 or 6 or 7 people doing each assignment. It just looks better when it's all in one setup. And in this case, I believe one of the deliverables maybe wasn't met. I can't remember on this one. Was I showing you that one? Let me see. Yeah, it looks like all the deliverables were met on this one. One of the other projects I looked at to show you guys, one person didn't participate and they didn't turn in the security. Well, the person that didn't participate, all these people on the team that don't participate, they get 0. I mean, it's real simple. I just need to know who didn't participate. In this case, the submitter said these 2 people didn't do it. So they got 0s, and in this case, wrong one. This case, oh, maybe this one. Yeah. I don't think they had any issues. Doesn't look like they had any issues on this case. All the members participated. Any questions? Did I cover it well enough to understand? Hi, Albert. You understand what you should be delivering? Yeah, I caught everybody. I thought you guys mentioned kind of what do I grade on? Let me look at that. I was going to look for that. I'd forgotten that. Project evaluation form. I mean, I told you it wasn't much of a form. What I typically do is I just look at the overview. And I look at process management, memory management, disk I/O, security, user interface, and then this is the whole. In other words, is it put together as a whole, complete document in the sense of it's being what I just said, it's being all of the same format, things of that nature. So that makes up 35 points. So if you divide 7 into 35, you get 5. So each one of these items would be 5 points. So when I'm grading, I think, okay, is this a 3, 4, or 5? Is this a 3, 4, or 5? Is this a 3, 4, or 5? Now, if one is missing, and that could happen because the person didn't deliver, if one is missing, I always just put a 5 anyway. Okay? So I give a 5 to that item that's missing so that the other members don't get hurt by that being missing. Any questions? Well, because there's usually quite a bit of work done on this, I grade it fairly lightly in the sense of I don't punish people if they're a little mistaken on some of these things. I just look at it, well, how much work did you put in? If I see a lot of copying from the internet, I get a little concerned. And once again, I say, if you copy anything from anywhere that isn't your words yourself, you need to quote them and reference them. And if I do find that a whole article like disk and I/O management is copied, everything's copied from the internet and presented as that student's work, then I would give a 0 to that. Now, that person would get the 0, guys. The rest of the team, I would add the 5 and add 5 for that for the rest of the team. So I don't punish the team for an individual's indiscretion. But I reward the team when the team does a good job on all items. Okay? I guess I should show, see, this is 2 years ago, and this was last year. I want to present it something like this. when your team leaders, when you submit them, you tell me your team and what you're doing. Okay, on the submittal, when you submit the document or PDF. Let's look at Team 5. I can't remember what that one was. This one was, 9 pages. Wow. There wasn't much to this one. It's only 9 pages, as you can see. So there was a lot of issues apparently on this team. So let's see if that's the case. Yeah. Yeah, they're missing some stuff. Anyway, there's one. So that they didn't get as much as they could have gotten. Oh, a lot of you guys are doing Mac OS, so let's take a look at Mac OS. Once again, I want to know who's doing what. And this one was 27 pages. Let's go to the end. And I don't see references. So that would be the document as a whole. If there's no references, and I don't see any references in here at all. So when I'm grading something like this, it would go as a whole. The references would go in here, and they wouldn't get a full 5 points. They may not even get 4 points because none of this stuff is being referenced. Got the idea? Okay, very good. I'm just close them up so I don't have anything open. All right, I'll hold on to that in case you have questions. Okay, I just finished discussing the project. I reviewed the team member list. I know what you guys are doing. I think it's going to be wonderful to see your results. I was going to review the optional programming project. If somebody wants to do that, I can do that towards the end of the night. We'll answer the CC Confer question on Thursday. I want to discuss this after we talk about Chapter 12. We should do this now. The final exam questions. You get to write the final exam, and I think I put the list. Chapter to student final exam. It's this list. Okay. And the list numbers are incorrect. What do you mean the list numbers? There is no chapter 26. Oh, yeah. I got that from, yeah, Excel. Yeah, I didn't spot that. Thanks. I'll correct that. Let me see what I did here. Because I thought I did those the other day. And that would be the final stuff. Let's take a look at that real quick. Chapter to students. Yes, this. That's the document. Oh, I probably uploaded the wrong one. But this is the correct one. So let me make a note to reload that up there for you guys. But that's the chapters. So what you're going to do is I'm going to, on Canvas, I haven't done it yet, but on Canvas, put a discussion, and I want you to use the reply to that discussion only. Don't create your own discussion. So I'll have it, it'll say final exam, it'll be on here, it'll be a new discussion. It'll probably be right on the top here. That's a new discussion called final exam model. You'll open that discussion and reply. And you'll reply with your questions following the model. Any questions on that? What you're going to do is, I'll show you an example of that. What you're going to do is write 3 for that chapter that I assigned you. So I'm going to put it in the final exam questions. You're going to write 3 multiple choice questions. Each has 5 choices, of which only one is true or correct. In other words, I don't want multiple choices. There's only one possible answer. So the format is you're going to put the question number, the chapter it came from, your name, and it can be your first name, and then finally the question itself, okay, followed by your answers. And you'll see the format when I give it to you. All right. And you need to indicate. Now I'll describe how you indicate when I give you the message. So you're going to indicate the correct answer. So everybody knows and they can check it. What I want you guys to do after you submit your questions is to review them, because I'm going to review them, and out of the 3 questions I'm going to pick at least one of them to be on the final exam. I might pick 2 or I might pick all 3. And if you, let's go back to the chapters. Let me give you an example of what could happen. It could be that Albert doesn't put us any questions, or Neil doesn't give us any questions. Well, I will supply my question and you won't know what that is in advance. So it's really pretty critical that people put them in, because then you'll at least see the exam questions. If they don't put it in, I'll put mine in. And you've seen my multiple choice questions on the test. You know, the kind of questions that I ask. We'll review these before the final exam. I'll tell you if I didn't pick one or not. I'll say, hey, you know, I didn't pick this question as we review them. Then what happens is I will allow these to be switched during the test. In other words, when you read the question, you're going to say, oh, that was A. Well, that's not the case. I will do the automatic shuffling of answers, so you won't know. You'll have to actually read the answer. So in that case, you can use, or you cannot use, something like all of these as an answer, because that would violate only one is correct. Okay, so you cannot use all of these, but you could use none of these. So in other words, none of the other answers are correct, so that one is correct. And it could appear anywhere since I'm sorting them. It could be, none of the answers could be here if you elected that. I'm hoping that what I'm saying is clear to you guys. Are you understanding me? Thanks, Megan. Thanks, Dan. Do you have any questions? So what you would do is, for the chapter that I assigned you, you'll write these questions and submit them, and you'll see them on the final exam. Now, occasionally I might have to, yes, lecture content, book content, since they're coming from that section of the book, I would think that whatever we were discussing at the time would be fair for that chapter. Yeah. Yeah. So the final is all multiple choice. That's correct, Megan. There are 44 questions. Yeah, I figured by the time you got to the final, you know, and if you participate along with this, you're going to learn. The whole object is to learn. So you're going to learn by doing these questions. You're going to learn when you see the questions. And you're going to have an opportunity to earn more points, because I'm going to have, if you look at the final exam, maybe I hid it. Maybe I hid it. Hang on a second. I might have hidden it because I do things like that. So let me look. No, it's hidden. You don't see it, but it will be there. You'll have an opportunity to earn 7 points in an optional test. Like we have our this week we have test 3. There's 2 tests. This is the only way I can do optional. Is the test has 45 points and the optional is worth 5 points. It's the only way in Canvas I can give this kind of concept of extra credit in an optional. So I have the same thing for the final exam. Is I have my questions, and I'm hoping that I get 44 good questions from you guys covering all the chapters we've done. Like I said, if we don't get the 44, I'll be adding mine, which you won't get a chance to see until the final exam. Now, once again, the final exam is Tuesday in room ATC 203, area D, from 6 to 8. And it's a 2-hour time limit. It won't take you 2 hours to do 44 and 7 questions. You're not going to use your own Kang. You're going to get there a little bit earlier if you've never been on campus for your account, and you're going to create your account. It's really easy to create your account, and you'll have access to this canvas. You will not be able to go onto the internet to search out internet stuff. And if you guys twist my arm, I may allow you to have a sheet of notes if you'd like to have one sheet of notes. I've done this in the past where you can have one sheet of handwritten notes. It can't be computer shrunken down the book. It can't be that. You can have one sheet of handwritten notes, which you will show Mary when you sign in with your name and your ID. Because Mary will check you in, and then you could show her, well, this is my notes. It's not open book. It's only that one note. Because you're supposedly have studied for the final exam. And what I certainly don't want you to do is to have a printout of all of the final questions, because what's going to happen is that discussion that we went through that has all the questions and the answers, remember that discussion? I'm going to delete it, so it won't be available during the final exam. That would be silly. Actually, I'd probably hide it. I probably won't delete it. I'll hide it so you can't access it. Okay? You got good questions. Yeah, I will allow the note. I typically do. So you can have one page, 8.5 by 11. You can't bring a legal-sized piece of paper. But you can have anything you want on it, as long as you hand wrote it. You can't shrink down any computer printed output. It has to be handwritten. Okay? And I'm going to explain all that to Mary. And she's done this before the last couple of years. So she knows how to administer my tests for me. Okay. Well, we'll review all of this, the week before the exam, okay? On that Thursday. What Thursday would that be? Week 11. It would be this week that we talk about encryption and stuff. That Thursday, I will go through and review the final exam stuff. Everything I just went over with you. Okay? We're in week 8 right now. Okay, let's go back to the agenda. I think we're doing pretty well. So when you see that, I'll have it out probably tomorrow. I'll have this discussion. You would reply to the discussion with your 3 questions. Now you need to get that to me by a certain time so that we can review this. So let's check that. That's in the syllabus. That's in the class syllabus here. On the schedule. Submit final exam questions. March 13th. I need them by March 13th so that the week that we're going to be reviewing the final exam questions here this week, I need to select them. So you've got to have them in by the 13th. Well, that's not really the end of that week. Let me see. 15th. Looks like the 15th. Final exam questions by the 15th. Okay, so I'm going to put that in our note too. So we need these. Need these by 3:15. Let me verify that, because usually it's a Sunday. I try to get these in. So 15th is Thursday, but I need time to look at them and have them ready for this week. So yeah, 15th. I need it by the 15th. If I don't get them by the 15th, I'll put my own questions in by the 15th. Okay? It shouldn't take too long to write these questions. Okay. That covered that pretty well. Over that, let's discuss Chapter 12. File System Implementation. So the first chapter was Chapter 10, which was mass storage devices and how they work, and RAID and that kind of stuff. Chapter 11 was file system concepts and how you create a file system and you format it and you set it up, and you have directories and all of that kind of structure. This chapter is file system implementation. How do you actually work on the secondary storage device? How are you going to manage that? That's what this is about. So you're talking about the structure, the implementation. How do you actually do the directory stuff? What are some of the allocation methods? How do you manage free space? What about how efficient and performance issues? What about recovery? And then he spends a lot of time on network file systems, and then this lawful file system. So let's take a look at that. Typically, it's a logical unit. When you think of a file, you think like, here's a program here, this PowerPoint, and it's presenting the contents of that file in some sort of logical way. So that's kind of how you think of a file. It's typically a string of collected or collection of related information. And it usually resides on secondary storage disks of some kind, or flash drives, or SSDs, solid-state devices, SSDs, solid-state devices. File system organized into layers, and there's usually a file control block that describes the contents of a file. So here's our layered file system. We've got our application programs like PowerPoint, and it's got a logical file system that opens, and then there's a file organization module. That's your access method, and then, or your API, your access method or your API, and then you have your basic file system. And typically this was set up in ROM on your computer, and then finally you have your physical I/O and actually on your devices. So that's a typical layer. When you were installing Windows many years ago, during one of the installations of the older operating systems like XP, and I can't remember if I did it with Windows or Vista, Windows 7 or Vista, but I kind of remember it with XT. You would see how it was installing stuff, and one of the things it was installing was the HAL, the hardware abstract layer, and that's what it's installing, is this stuff right here. A typical file control block has these items in it: file permissions, file dates, access, file size. I think we might have mentioned that before. You also have part of your file system structure stored in memory. And let's take a look at those. So you would have in your user space, you'd have your open file, and in the directory structure in the kernel memory, you would have pointers to the physical directory and the file control blocks for that that's in storage. Okay, and then when you read it, the system table, you would have a pointer, but what it doesn't show here in this is in your program space, you typically have a buffer for the file. This has the pointer, but it doesn't show the buffer of where it puts the data in your user space. This diagram doesn't show that, but it is. It's attached to your user space. Then virtual file systems, right? So you can implement different file systems. So it's another layer. And it looks like this. Your program is speaking in one interface, and then it goes to the file system interface and figures out which file system type that is. Is it an EXT? Is it a NTFS? Is it a FAT32, etc.? I think we talked about this last time in chapter 11, but how you implement your directory. You got your linear list concept, where you can have file names with pointers to data blocks, or you can have a hash table concept. And I think I illustrated this hash table when we were talking about direct access. Now, this is kind of the fun part of this chapter. An allocation method refers to how disks are allocated for files. And remember what a disk looks like. You got a bunch of sectors, right, on tracks. You got a bunch of sectors, and you have different platters, and you have the geometry, right, that could be sequentially allocated blocks of data. All right, and so they could be contiguous blocks. So on your disk, they're contiguous. Or you could use a linked allocation scheme to have pointers to different sections. Or you could an indexed allocation. So you have some kind of a block that's an index to other blocks. So these are the different allocation methods that you could use for your files. So let's look at contiguous. So each file occupies a set of contiguous blocks on the disk. The kind of nice thing, I guess, about this one is you could read a file pretty quickly without moving that that read-write head, right? We talked about that. You could do a cylinder boundary, where you're reading the top surface of this platter and the bottom surface of platter 1, the top surface of platter 2, the bottom surface of platter 2. So those 4 surfaces could make up your cylinder, right? And that has all the tracks as it's going around. That has the track as you're going around. You're picking up all the sectors. So for performance reasons, when you read a file using contiguous allocation, it's going to be pretty quick. Let's see what you can have. A simple structure. You just need the starting block number and the number of blocks required. You could implement random access. However, you get a wasteful space dynamic storage allocation problem. The files can't grow. If you think about it, let's say I allocated a whole track, right, all 4 surfaces to a file, and then I can't add to that file if my next track is also allocated to a different file. So I have all kinds of issues on file growth. And I can't really, if I dynamically add to the file, I would be constantly moving it, copying it to a new area that I need more space on. So these two things are pretty harsh in this allocation scheme. And they're giving you an example. And you might see these examples on the test. The count starts at 0, this count file, and it's got 2 blocks. This TR starts at 14, it's got 3 blocks. Mail starts at 19, and it's got 6 blocks. So if TR needed to grow, let's say, needed to grow 3 blocks, it can't. So what happens in this kind of scheme is the same issue we had when we were allocating memory. And we were doing it contiguous allocation. We would have to burp the memory. You remember that? Well, in this case, we would have to reorganize the disk to free up these free blocks so we have enough space to allocate more blocks to TR so that it could write those blocks. Now, think about the issue of when I condense this space, what happens to the files that are currently opened by other programs? Well, we'd have to stop those programs because we're going to reorganize the disk. So there's quite a few issues with this type of allocation. Not that it's not bad, it's just you need to know those kinds of things. I want to stop here because I want to bring in an example. If we're using this kind of scheme, this fits perfectly on the mainframe. There was something called a partition data set. And the partition data set, you gave it a certain number of blocks, just like this. Matter of fact, this looks just like a partition data set. In the case of the mainframe, it was considered a file, and it was contiguous, something contiguous like this, where you would have files inside the partition. That's why it's called a partition data set, a PDF, a partition file. It was files, and then things freed up, a file freed up, and you wrote another file and another file. So you could have many files inside your partition data set, your PDFs. And eventually, you run out of free blocks, and you have to offload that partition and then reload it back so you can gain free space. And that's exactly what you had to do. And it's very similar to having the whole disk do something just like that. And then there's the concept of adding extents, right? Okay. So the idea of extents is when the thing fills up, you add either another disk to it or more empty disks. So you have extents. The next allocation is linked, where you have a pointer to a block. And this looks like this. This is pretty cool, this linked allocation method. You would have a starting point. So file G starts at 9. There's the pointer. And the next block is at 1. Let's see. No, the next block points to 16. So there's a pointer in the data. So the next block is pointing to 16, and that block is pointing to block 1. Block 1 is pointing to 2, and 2 is pointing to 25. And that's the end pointer. Okay, so this guy has, and it has a number, -1, which means I guess that's the end of the chain. I'm trying to think here why these numbers inside don't match up right. I would think this would be block 1, this would be block 2, this would be block 3, this would be block 4, this would be block 5. And that would be the kind of question I would have with you. I wouldn't show you the arrows, but I would tell you inside here which is the next block. I'd give you the pointer or something. Are you following this okay, guys? Good. Okay, this one you're going to definitely see on the test again, because it's a fun way of doing something. And it was the original DOS concept, was this file allocation table or FAT table. And the idea is you have a directory entry that has a pointer for each of your files. You would have a pointer to where the block started. So this test is the file. It has some bits about it, protection bits, access bits, that kind of stuff. And then it would have the block pointer. And in the actual file allocation table, you would go to that offset, 217. And it would have either an end, you know, like all ones or something, which means it's ended, or it would have maybe all zeros or something, it says it's end, or it had another number, another offset. So it would go to 618, and now 618 goes to 331, and that's the empty guy. So it's, you know, there isn't any further parts of that file. So these blocks, there's 1, 2, 3 blocks. And that would be the kind of question I'd ask you if I wouldn't have all these arrows. I would just have the allocation table show you the pointer and ask how many blocks are in that file. And you would tell me. Now each block represented a cluster. And a cluster would be, let me think here, a cluster would be either 8 or 16 sectors. And a sector, if you recall our previous discussion, a sector was half a K. So I think there were 16 sectors, so that would be 8K. So each block was 8K. So it would, if you didn't use all that 8K, you would have a waste fragmentation, yeah, of that block of data. Just like in memory. Okay, the last method is it puts all the pointers together in one block. So let's take a look at this. So what we would do is we'd have our file G, we'd have our index block 19, and 19 would have all of the other pointers. So the first one is 9, the second one is 16, 1, 10, and 25, and the other pointers are empty. There isn't any. And this method works pretty well, except how many the length of the file, the size of the file. Let me put it that way. The size of the file depends on how much you can get into this index. Okay, for your blocks, whatever your block size is, when your block is 8K each or whatever. So there's some limitation here. There was limitation as well here. The original fact table was 12 bits. 12 bits. So 2 to the 12 is 4K. So 4,000 blocks was what was available to be allocated. That would be the maximum allocation blocks, and then depending on your block size would be how much you could allocate on that particular file system on that disk. Okay. I'm going to skip the algorithms. It's just, to me it's easier to see that diagram. So I have my file pointer, right? I got my file pointer. It points to my outer index. And then I have an index table that points to my blocks of my file. And this is pretty common, this structure. It's not difficult to implement. And that's what Unix uses. This concept really got used in Unix. And it's 3 layers deep and 4K bytes per block. I told you that already. And so you could have in your index structure here, you could have your data blocks for the file. So the concept here was you can have a simple access to your data files if they're small by having direct links. Then, if it started to grow, you would have, your first would be a single indirect where you have your index and then your pointers to the data files in that index. Okay, you can have a lot here, but they're only showing 2. And then if your file exceeds that, you would go to a double index where you have an index block and another index block and another index block. So you're basically taking another power to how many you can store. And finally, the triple is triple. You would have an index to an index to an index to data, and that file could be very huge file. Some of the schemes have to do with, well, how do you make a file big? Okay, any questions on those 3 types? I know there are going to be some questions. I told you about that on the test. There'll be some questions about these 3. So I want you to understand them. Okay. The next topic is free space. How do you keep track of free space? And Windows uses this concept of having a bit to represent whether the block is available or not, to keep track of all the blocks. And yeah, I'm pretty sure Windows uses this concept. And it copies this block into memory, and it has to make sure that it stays in sync with what's really on the disk. Otherwise, you're going to run into a lot of problems. If you allocate a block and you don't indicate that block has been filled, and let's say the system crashes or something, I believe, let me think this through, I believe it keeps 2 copies of the free block on disk. I could be wrong on that. I think NTF keeps 2 copies. Unix does it a little bit differently. It uses inodes to keep track of free space. Anyway, we can calculate block numbers pretty easily. You take the number of bits in a word, you know, if you're doing a 32-bit word or a 16-bit or 64-bit, whatever that is, times your number of values, and then add that to the offset. You could find this. Okay. So your bitmap of free space requires space, you know, to store it. It's easy to get contiguous files because you can look there and see which are free blocks. The other way is you could use a linked list. Okay, so the bitmap I showed you is pretty straightforward. Linked list, you can have another pointer that points to all the frees. You cannot get contiguous space as easily. But there's no waste of space. You're not wasting space. You can use a grouping concept where you can group clusters or blocks. And I think Unix uses that. I think we'll see that in a minute or two. I think I talked about it. In memory, did we talk about the buddy system in memory management? Yeah, I thought we did. That would be very similar concept of grouping, is like the buddy system in memory. We certainly need to protect this stuff. Okay. The pointer to the free list needs to be protected so that we have an accurate pointer. The bitmap must be kept on disk. A copy in memory and disk may differ. I talked about that. We cannot allow for block I to have a situation where bit I is 1 in memory and bit I is 0 on disk. Yeah, I said that. We can't allow for that. So when you do file allocations, you're putting a file, or let's say I make a change to this disk file here. What is it? PowerPoint chapter 12 or the old 11 PowerPoint. I make a change and I write this file back. This file is treated as a sequential file in terms of PowerPoint. So PowerPoint writes it as a binary file sequentially on disk. And when it's writing that on disk, it's taking whatever free space and flipping those bits every time it writes a block out there, or it could allocate that whole block on disk and start writing a whole block, or 3 blocks, or 4 blocks. They're all different strategies for doing this, but it's got to keep these in sync. And I'm just saying, there's a lot of specialty code going on to make this work properly. And by specialty code, I mean locks of some kind. Okay, now we could figure out how to do our directory. Well, you can have a linear list of file names with a pointer to the data blocks, right? Or you can have a hash table. And it depends on the file system as to how the directory structure is implemented. Some systems put the directory structure on disk at the very beginning, and they leave a certain amount of room for the directory structure on the disk, and it's a certain location in the file system. Others may have it spread throughout the file system itself. They have the directory structures. So they could be anywhere, depending on the design. Here's a free space list on a disk with linked. So, there's all the free spaces on the disk. But you don't want to ever lose this pointer, because that's the one that says this is the beginning, right? So you would probably have a head and tail queue, would be my guess, if I were going to design something like this. And I would have a head and tail on that block that's free, so I know that the next free one. Matter of fact, if you do any kind of a linked list, you'd probably have a head and tail concept. All right, now let's look at some of these ideas for efficiency and performance. You can disk cache, so you can separate a section of main memory for frequently used blocks, you would have a disk cache. Now, most of your disks have memory caching on the disk, and that's what when you buy a disk, it usually says, you know, how much cache is hardware cache is on that disk, and you can take some of that caching block that's on the disk and put it in main memory, and that's what they're kind of talking about. You could have free behind and read ahead to optimize sequential access. So as you're going through this cache, you're reading ahead and you're freeing. So it's kind of like a circular concept where you're freeing ahead and freeing the past stuff and reading the new stuff. So you stay ahead of the program that's reading sequential files. And a lot of programs, you know, like PowerPoint, it's reading sequential. There's only a few programs that do real offset stuff where the program's more efficient if it uses seeks inside of a file. Okay. Any questions so far? We're going to see pictures of this in a second. So a page cache uses pages rather than disk blocks. So the idea is you're going to use the memory management page concept. So you're going to use the size of a page, a virtual storage page in memory. So memory mapped I/O uses page caches. Because we're mapping it directly into memory, we might as well use page caching. Routines typically through the file system, they use buffer or disk caching. And this leads to the following figure. So let's take a look at that. It's easier, I think, to see in the picture. So without having a unified buffer cache, my I/O using reads and writes is using a buffer cache. A buffer cache is a block of memory. It may or may not be a page cache. In other words, same size as a page. This might be 2 pages or 3 pages. But that's what the file system uses to read and write directly into, and your program uses it. Let's come out here for a second. Did I illustrate this? Yeah, I have a data file organized by fixed size records. So I've got a social security number, and I've got a person's name, and and the person's name looks like it's 25 characters. It's this size. It's 25 characters in length. And then I have an earnings statement that could be $1 trillion, it looks like. Yeah, $1 trillion. So that's pretty good earnings for that person. And that would be the way the program wrote these records. And the cache is three records are a block of data. Okay, and then the next 3 records are the next block. So I'm reading this block into a cache, and if we go back to the design of our operating system. Remember that a user program has the program code area, it's got the data area, and it's got a system stack area. And that system stack area is where we save the state of the machine when it was taken out of the CPU. You recall that, guys? Are you remembering that? Thanks, Mega. Well, also in that system area is these buffers. So the buffers have these three records in them, and then when you did the read, the operating system knows the length of your logical record because it's got to declare structure or declare constant or data constant or DC or DS data storage that knows the length of this thing, and it can put that in your record in your program without doing a physical I/O. It does a logical I/O. It doesn't have to physically read from disk. So it could read these buffers, and that's what this was talking about here. Right here is this read and this buffer. This buffer cache is in that system area for your program. And once it's in the system area of your program, the next time you do an I/O request to read another record, it doesn't have to physically go down to the file system. All it has to do is read it from the buffer and put it into that data storage area that you had defined for that record. Is that clear? Yep. Thank you. Okay. Now, there's this concept where you use the same buffer. So your buffer cache is the same as your page cache, so that your memory mapped I/O can run, and your I/O can run as well. And that's pretty cool. And a lot of systems use this kind of concept. Okay, so I talked about those things. Now, recovery. This is the tough one. This is one that requires a lot of thinking. That's why I like RAID. I like RAID 5. I told you the RAID 5 story on the move when I was with Jetstream. Did I tell you that story? Not yet. Okay. I started as director at Jetstream in communications in 2000. They did voice over internet. They really didn't see it the right way. They made it 10 times more complicated. But at any rate, I was with the company for 2 years, and it kind of just went under. It was a startup. But when I joined them, they were really ramping up. They had a lot of venture capital, and they were moving from a smaller building to a much bigger facility. So they were moving from Los Gatos, where the owner of the company lived. It made sense, and they were moving to San Jose, right next to Google. Google just bought that property and was building when Jetstream moved just up the street from them. Let me think a second. So during the move, we had these probably 8 to 10 racked file servers, and I was there a month before the move, maybe 2 months before the move. And we did the move, and we put the rack of computers, because we didn't trust the movers. We put the rack of computers in our own truck and moved it, and set that rack up, and brought the old rack in, and re-racked them to the new racks that was built and ready for them. And then when we fired up, these were all XT computers in 2000. Windows XT, or NT, Windows NT, and might have been NT. I can't recall, but they were all RAID 5, and one of the servers didn't come up, and it came up with an I/O error of some kind, stating that it had an issue with disk X or whatever it was. So what we ended up doing was, since they were all RAID 5, we pulled the one that was bad out and put one in, and about 4 hours later rebuilt, when the system started up again, it rebuilt that drive, and we didn't lose a thing. On RAID 5, if you lose 2 disks, though, you're out. It can't do that. So that's my story about RAID 5. I'm a firm believer in backups, and we had a backup unit that was a tape drive that we backed up, and we had this really complex schedule, so that we always had a full backup from a week ago and all the supplementals, so every week, and then we would rotate these tapes so that we would have a month backup that wouldn't rotate, and we had a yearly backup that wouldn't rotate. So if we had to go back every, to 2 years or 3 years or something, 4 years, we would be able to go back and restore a file from that backup. So our backup system was pretty complex, and we had an off-site storage for them. The only thing we didn't have, which I was starting to build, was a backup, physical backup location. So we ended up designing, which I never tested, was we had a facility in Raleigh, North Carolina, and it was pretty close to our headquarters facility. So I prepared it to be able to do a recovery if we ever had a major earthquake or something in California there. But I never tested it. But that's what you want to do, is if you're going to have any kind of recovery. How often do you guys back up your files? Once a month, image monthly, every quarter. Okay. Have you tested it? Karen said yes, and she's tested it. Oh no, oh, you haven't. I smile. Oh, okay. Well, here's what I want you guys to do. Test it. Try to restore one file. All right? Test your backups. And you should do that, periodically, at least, once a year. Test to make sure that your backup works. I'll tell you a convoluted story in a minute. log structure, journaling, system reports, each one as a transaction. We kind of talked about this concept of starting a transaction, performing it, and then committing it. You remember that discussion? I can't recall where we... Oh, I remember. It was in Chapter 7. When we were kind of talking about deadlocks. Or Chapter 6, one of those chapters. 6, yeah. When we were talking about synchronizing things. Yes. The network file system, not going to really spend a lot of time on this. I'm not that excited about it, only because, you know, Sun is pretty much gone. There is that capability of the virtual file system, though. That does exist. And you can mount different structures of file systems on it. So that's worth talking about. Write anywhere file layout, that's Waffle. Write anywhere file layout. And it serves these different types of environments. I think I'm almost done here. Yeah, I'm pretty much done. Okay. Oh, here's the story. Did I tell you this story about the power failure on my Sun Spark system? I thought I did. Maybe not. Oh, I told you about it, didn't I? Okay. All right. So in Unix, it uses the inodes, part of a partition structure, and they have the capability to correct that on the partition. I had a Sun Spark 20 SCSI drives attached, 4 drives running in Formix database. You create a virtual volume when you build that system. The virtual volume identifies what on those 4 drives, what logical presentation that gets presented. We got a power failure and it affected the disk drives. There was a backup power unit, but for some reason it failed, and I don't remember why. So even if you have one of those backup battery units, test it. I obviously didn't test it here, but at this moment in time, my role was not the director of this. My role was I was the application manager, so I was responsible for making sure that the Informix application is running, not the box has power. There was a backup power unit for some reason. First, it wouldn't boot. So I detached the drives from the 20 and attached it to the Spark 10. Then I was able to access the drives, mounting it on the 10. So I restored them from the backups from last night, because we took backups every night of this database. And of course, every transaction that was done up to that point was lost. But we had them up and running to take orders. This was Arbor Software Company. They made S-Base. I don't know if you ever heard of S-Base. Multi-dimensional spreadsheet concept. Microsoft bought the license from it, and they also bought Fox Pro. Microsoft bought Fox Pro. So Microsoft has Fox Pro, they have S-Base, They call it multidimensional spreadsheets, but they have that product. It was a great product. Okay, so we talked about that. We talked about that. I think we talked about that last time. Okay, yeah, I copied this from last time. Okay, so here's a question to you guys. If I want to implement this concept of direct access, where I have a hashing algorithm that takes me to a specific offset in a file that has a pointer to a record in the file. So I'm using basic direct access method. What implementation on the disk makes the most sense to use? I thought I was all the way up there. See, where was that? Huh. Oh, yeah, here it is. Here it is. Do I use contiguous allocation, linked allocation, or indexed allocation? Which would make it work nicely? Bayo says indexed. Okay. Trying to make this so I can show you both of them. Okay, once again, I'm coming with a hashing algorithm that's going to come out with a number. And you think that index would be good. Possible. Dale, I would say you could possibly implement that. But I could do it faster if I didn't use index. Because if you use index, you gotta first chase the index. See, I've got the block of data stored at some offset from the beginning of the file. So I would have to, in order to do it with indexes, I would have to run the algorithm that gives me an offset, read that indexed offset, and then read that block. And that seems like an awful lot of reads to me for direct access. Is there another one that might be faster? Anybody? Yes, mega, contiguous. If you really wanted to implement direct access, you would do it with contiguous allocation. It would be the fastest. Now, it's with this scheme, though, the way it would work would be you have limits here. In other words, how many data records you can actually access in this scheme. You would have those same kinds of issues for contiguous allocation. Okay, let me ask you another one. File organization. We just did direct access. What about sequential access? What would be a good mechanism for sequential access? Which of these three? Contiguous? Dale? Yeah, that would be okay. But the problem with contiguous in this case is when the file grows, it's not, you're not doing direct access, you're doing sequential. So linked would be a good mechanism. Linked would be a good mechanism for sequential. Because it can grow really easily. And typically, remember what I said about these files, when I make a change here to this PowerPoint, or even this document, when I make a change to this document and I save it, the old one, the old file, who knows what the blocks are going to be like when it replaces it. It might just write over the old file and add to the end of that if it has space. More likely, it would basically mark the old file as unallocated and free those blocks up and stick it somewhere else. That would be more likely. And there's a, let me think a second on this. In the control panel, no, I don't want the control panel. I want, oh yeah, I think they're under Windows. Let's see. I was looking for the disk management one that will compress your disk. I don't see it right now. I'd have to look at it later. I'll look at it later. Maybe next time. We'll take a look at it. The last one is index sequential. Anybody have a guess? What would be good for index sequential? Which of the yeah, index allocation? Yeah, the same word. Okay, what I want you to understand, guys, is on the test I might have a question that says, kind of describe this environment. Like if you're going to have a file organization. Now remember, this is logical, this is physical. Which would you use and why? Okay? Just in case I had a question. Alright, let's see where we are now. We discussed all of that. I did go over the file allocation table with you guys and described it to you and told you the type of question you would see on the test. And I'll review the test on Thursday, right? All right, I went over all of that. Let me see. Do you have any questions on anything we've discussed, or? We have, if you're interested in doing the optional programming project, and you have a question, I can stick around for that. Otherwise, I think we're pretty much done for tonight. So, questions? Yes, we have exam review on Thursday. So I'm hoping to make it brief. I'll probably tell you another story. I've got a few that are kind of fun in experience I've had. But to do the review, we should be pretty much done in an hour, maybe an hour and a half at most on Thursday. We'll see. I say that, but I always talk. So. And I'm going to go over this one and this one. And this one is going to take some time, so maybe it will take time to explain. Because if you could do this optional problem, you really understand the concept of the operating system and what it does. Okay. It depends on where you're putting it, right? Let's just take a look real quick. That's chapter 12, right? Oh, this one. Okay, so a file is currently consisting of 100 blocks. Okay, so the file control block and the index block are already been read. Okay, so we don't need to count those. How many disk operations are required for contiguous? Let's try contiguous first. A block is added at the beginning. All right? So if it's added at the beginning, don't you have to read the other 100 blocks? Right? You're going to add them, so you're going to put them somewhere else. You're going to have to, allocate another 101 blocks. So, does it say read or write? How many disk I/O? So both read and write. So you're going to say, I'm going to read 100 of them. I'm going to write 101 of them. So it sounds like 201. Okay. What about block? Let's contiguous. The block is added in the middle. You're going to read, yeah, you're right. You're going to read 50 and write 51. So you got it. 101. Yeah, because you're really going to, if you add it in the middle, right, you gotta somehow read the 50 that you're going to basically move, and then you're going to write the one you're writing first, and then write the other 50 back. So you've got to read the make sure I got that. This index allocation. You got to read the index, so that's one. And they said they read it, and I'm going to write. I got to write the index block, and then I've got to write the data block. And then if you're doing forward and backward pointers, you're gonna, the two blocks that it used to point to, you got to fix those. So I'm counting 3 or 4 reads and writes. I got to think a little bit more on that. Sounds like 3 to me. If we're adding in the middle. One, to read the block itself. You got to write the new block back in. Write that. Yeah, so I'd say 3. That's what it sounds like. No, that's contiguous. That's not true of indexed. Allocation. You can insert an index in the middle or in the front, so it has room to grow. Okay, well, let's try the last one. If the block is removed from the end, what do you have to do if it's contiguous? Yeah, you could. I'm responding to your nothing. If it's contiguous and you're using contiguous allocation, remember it has the pointer to the beginning of the block and the number of blocks. So all you would really have to do is change the number of blocks on the file control block, which is already in memory. So I would kind of agree with you on that if it's using that technique. If it's using some other technique, then I would venture to say that it would go somewhere else. That you would copy it and put it somewhere else. So basically, you would read 99 and write 99 somewhere else for 198. So I would probably accept either answer. Yeah, if you have a question on these, we can also review them on Thursday, right? If you haven't done them. Yeah, this is a pretty straightforward question. Same with that. Oh, this is fun. You have to kind of think about this one, but it's a fun one. And that's not 11, that's 12. That's 12. So I made a mistake here. I have to fix that. I just noticed that. Remember I told you these chapters changed in the new book. Okay. I think we're pretty much wrapping up. I hope it's clear tonight. You had about all the things we discussed a lot. If you have any questions, just use an email or discussion. And I want to wish you guys a great evening. And I'll see you on Thursday for our review. And thank you for participating. Have a good night, gang. Dale, have a good one. Good night, Albert, Daniel, Karen, and Steve.